Hi, everyone, and thanks for joining us again for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. We can measure how much phosphorus applied as fertilizer is used by a given crop using a few different methods. The gold standard involves using radioactive isotopes of phosphorus to trace its movement from soil through the plant, but this method is costly and carries with it environmental risks. As a result, we often calculate phosphorus use efficiency more indirectly. These indirect measures have implications for how we manage phosphorus, but how accurate are they? We're joined again today by friend of the show and colleague Dr. Andrew Margenot from my alma mater, the University of Illinois at Urbana-Champaign, and he'll discuss his new agricultural and environmental letters paper on the topic. Well, thanks again, Andrew, for joining us for Phosphorus Science Now. I think you hold the record now for most appearances on the show, and we're big fans of your research, so it's great to see another great paper come out of your lab.
Thanks, Matt. Thanks for having me back and for putting up with me for a third time.
It's easy. Do you want to just launch into it?
Sure thing. So I'm happy to share this recent publication from our group, which is myself, as well as with Neha Chatterjee and Chungyang Lee. This was sponsored by a combination of Illinois NREG and US NSF. And as you can see here from the paper, from the screenshot, our goal was to understand what we hypothesize as discrepancies between how we measure phosphorus fertilizer use efficiency. There's two major methods that we compared, and to summarize it, we expected that one would overestimate compared to the other. I want to now walk you through the rationale for this work. So perhaps the first question is, what is PUE and why would we care? So PUE is the acronym for phosphorus use efficiency. Typically, it is in the context of agriculture and in reference to a fertilizer. It could also be for manure, but really an input, an addition of phosphorus to the agro ecosystem. And we care about it because the underlying concept is how much of what we're adding to the cropping system is being used by the crop to produce biomass. Whether that's for fiber or food, that's a different question. Efficiency makes sense, right? We want to be efficient with resources, be it irrigation water, be it with energy, with time, etc. In that sense, PUE is no different, excuse me. What is different is that there are multiple ways of calculating PUE. And these different ways may give us different values, which can be a little bit confusing, even awkward, when we're comparing apples to oranges across studies. So there's three problems presented by having the low PUE that I want to briefly touch on. This is part of the why would we care about phosphorus use efficiency, and specifically why would we care about having too low a PUE. So the first of three problems is that it's an economic loss. There are investments made by farmers and producers to buy the phosphorus as a fertilizer and to apply it. So the question that we often hear from farmers in the Corn Belt is the phosphorus that I'm applying paying for itself? And not really the yield, but the dollars net per acre that resulted from the yield increase. And this is important because, well, as you may have heard, the price ratio of corn to fertilizer is at its peak in the past 4 years, as shown on the right-hand graph. And this has triggered a lot of questions by extension land grant offices like the one shown here on the left of, is it even worth buying phosphorus this year? And the answer is that if you have adequate soil test phosphorus, it may not be economically worth applying phosphorus. So the first reason to care about low PUE and to get a high PUE is that it's more economic to have high PUE. The second is that we avoid legacy phosphorus or this residual phosphorus built up in soils, as depicted here in the map as the yellow to dark red. The yellow to dark red would be a P surplus, which is a different way of saying a low PUE happened. We added more P than what was taken off with crop harvest, so there's a positive balance. It built up as a surplus. That is low PUE as a result. And when we have this buildup, this legacy phosphorus in soils, there are associated risks of off-farm losses, largely as runoff, but also by leaching. And the third reason to care about low PUE is that long term, we are going to run out of phosphorus that is economically viable to mine unless there's a breakthrough in the mining, kind of like fracking with oil deposits. So there's still reason to care about phosphorus. I don't agree with the peak phosphorus concept, but I do agree with the concept of the volatility of phosphorus prices as there's increasing scarcity of economically viable deposits. And so, if we think about global trends in phosphate prices, either from the ore of phosphate rock to these synthesized phosphorus products that result from the ore, there had been historically high peaks in prices, which can cause real issues in accessibility to farmers worldwide. And overall, the forecast is more volatility in phosphorus fertilizer prices. Because of that, it makes sense to be as efficient as we can in the phosphorus inputs that we're purchasing. So now to the focus of this paper, which is how do we calculate PUE? And more specifically, is the way that we calculate it going to give us differences in the net outcome, in the net value? So can I think about my percent use efficiency in the same way, depending on how I measure it? There's three specific methods that can be devised or divided, excuse me, into two ways. The first two are the indirect approach. The first of these is the PUE by difference. So subscript here for difference. This is the equation. And the concept is that we have a P unfertilized control and a P fertilized control. We measure the amount of phosphorus in the crop without any P added to the soil versus the P in the crop with phosphorus added. And the idea then is that we are subtracting the soil-derived phosphorus from the soil plus the fertilizer derived phosphorus on the left. And then we divide this by how much P was applied in the first place. And that as a percent would be PUE by difference. In some cases, when there's no data, excuse me, before I get into that, the key assumption here that I want to highlight that we test is that the P uptake in the crop without any P fertilization is the same as the P uptake by that same crop species when there's P fertilizer present. That's the key assumption here to do that one-to-one subtraction. Now, in some cases, we don't have crop P uptake without a control, in which case we have the balance method. This is more common for, say, county or state or national inventories of PUE. And in this case, we simply divide the P uptake by the P applied. And as you might imagine, there could be issues with this, namely that we don't account for the soil contributions. And yes, some of the soil P is derived from past fertilizer, but when we're discussing the PUE of what we applied in that season, then this has a potential artifact of overestimating PUE by counting soil derived as fertilizer derived. Now, for relative comparisons, it works, and sometimes it's the best we can do, especially at, say, global study scale.
Andrew,
These,
just to clarify, so in that first equation, I just want to make sure we understand this. So the what you're saying is the soil contribution in the fertilized versus the unfertilized samples would be the same. It's just the fertilized part is different between the two, correct?
that's correct.
Great,
That's
thanks.
the assumption being made.
Thank you.
You're welcome. These then are the two indirect approaches. The third approach is direct, which is using isotopes. So for this, we can use 33P or 32P. These are radioisotopes, which means that they give us extremely high sensitivity. We're counting individual atoms of phosphorus decaying with the half-life of 25 days for 33P or 14 days for 32P. And what we're doing is that we are synthesizing a fertilizer and we're labeling it radioisotopically. So we're measuring directly the fertilizer phosphorus by virtue of the label in the crop divided by how much we added. Hence the direct approach. This arguably is the quote unquote real PUE. Now, if we think about is there any evidence to anticipate why these three methods may differ? Well, we do know between the two indirect methods that there are pretty salient discrepancies. And as an example of this, there's a phenomenal paper by Dr. Dillon from 2017 that I love to read because it has a graph like this. You've got on the left-hand y-axis PUE by balance, and on the right-hand axis the PUE by the difference approach. A few things to note. One is that the mean PUE globally for cereal crops that they estimate over this time period is 77% for the balance method. The same data set or the same time period for the same global cereal crop approach is 16% for PUE by difference. So that's a pretty big discrepancy by a factor of five. But also note that PUE by balance exceeds 100%. Now, this makes sense because, again, the PUE by balance does not account for soil derived. So, if the crop took up all of the fertilizer P and then some from the soil, you could imagine how there's more P uptake than P applied. And hence, the balance method can yield over 100% PUE. So, that obviously doesn't make sense ontologically, it makes sense mathematically. This then is an example of evidence that, yes, the method of determining PUE may lead to discrepancies in the values. They may not be comparable, as in this example of a 5x discrepancy. So for our work, we wanted to do a proof of concept that would compare the two more commonly used methods of PUE by difference versus PUE by isotope. And for this, we chose three soils from Illinois that represent the major soil types of the state in the Corn Belt, mollisols and alpha sols. And we intentionally chose these to be adequate in soil phosphorus, meaning that they are above the critical soil test value of 25 ppm. I'm not going to call this high available P because Melic 3P, like any soil test, is not availability. It's simply a way to predict crop yield response to P. There's a key nuance there. The point, though, is that these soils represent what farmers are doing. This is realistic. Farmers are not letting their soil test values fall below the threshold of deficiency in general. And second, it allows us to test a hypothesis that the discrepancy between these two methods will widen. It'll be larger in value difference as you have a higher amount of soil melic 3P because there's more P in the system. And so the uptake of the P unfertilized crop will not be the same as the P fertilized crop. Again, that's the central assumption in the PUE by difference approach. So these soils are typical of what we see with melic P above 25 ppm, going from 30 to 83 ppm. We added P at the same exact rates, which is a maintenance rate for a 2-year corn soybean crop rotation. Again, we're trying to mimic a farming practice, even though we're in the greenhouse. And we used two different forms that differ in solubility to also test the hypothesis that higher solubility MAP will have higher PUE than the lower solubility struvite, which is also an ammonium phosphate. And in the Corn Belt, the major source of P being applied to fields is ammonium phosphates, typically MAP and DAP. We grew corn to V7, maize to V7 stage because one, theoretically, this is defensible as a period of high P sensitivity. We know that if the crop senses any P limitations, it'll typically constrain future yield potential, even if there's alleviation of P deficiency later in the season. And second is the practical reality of radioisotopes. We have a pretty short half-life. And so going to a longer duration is tough, especially in the greenhouse because of root binding effects. And in the field, it's challenging because it's radioactive. And so we can't simply use radioactive materials in the field that are open.
Andrew, just for people who aren't familiar with the terminology, V7, that's a pretty short plant, right? We're talking about how tall.
Great point, Matt. Excuse me. So that means the seventh true leaf stage for V is for vegetative stage. This would be corn that would be, oh gosh, 7 to maybe 10 inches tall.
Right.
It's definitely not the knee-high corn that you think of. So it's not baby corn, but it's not teenage corn. I'd call it preteen corn.
Great, thanks.
Sure thing. Okay, so as a bit of background from a separate study with the same experimental design, we found that in the same soils, under these two different sources of phosphorus, which shown here, green is the MAP and blue is the struvite for the same three soils, we found that the biomass and the P uptake by corn was the same. So there's no difference in growth. The corn is the same height, the same biomass, the same P uptake in terms of the amount of P per plant. And the graph here, what it's showing you is that the amount of phosphorus from the fertilizer, the percent, did differ by soil and by the source. So this is setting the stage for the PUE question. And what we're finding is that there was more phosphorus uptake by the corn plant coming from the MAP than from the struvite. But regardless of the fertilizer source, we're finding that less than 30% on average is coming from fertilizer by the V7 stage of corn. So in these soils that are receiving a maintenance application of P because the soil test indicates adequacy, the majority of phosphorus is soil derived. That's the first thing to keep in mind. So meaning soils are 70 to 90% of the P uptake at this early pre-teen stage of corn growth. And it's higher for MAP than it is for struvite, as we might expect. Okay. So now let's look at the PUE data from the current paper that we're discussing. So what I'm going to show you is the three soils from left to right. And we've got on the left-hand side PUE by difference as a percent. And yes, that axis goes negative. I'm going to indicate that more clearly there. And on the right-hand side is PUE by isotope, which does not go into the negative. In green, we have MAP, the higher solubility P source. In blue, we have struvite. So what we're doing here, let's begin with the PUE by difference. We find that overall, we get largely negative values. So if we look closely compared to the PUE by isotope, where the values are above the zero line, we get negative PUE percentages by difference. We do not see that with the PUE by isotope. So that's the first major finding. PUE by the isotopic method directly is positive, and it was higher than PUE by difference. We find that the majority of observations for PUE by difference are negative. Three-fourths of them were under the 0% PUE. They were only positive for one soil and only for MAP, the higher solubility P source. So the question is raised, how can PUE be negative? And so just like PUE by balance exceeding 100%, same goes for PUE by difference. It can be negative. Ontologically, that's impossible. But mathematically, of course it's possible. If we look at the equation shown below, all we're saying is that there was more P uptake when the corn had no P applied than when the corn had P applied. And this is, as a result, telling us two things. One is that the assumption that P uptake, if the crop has no P added versus if the crop has P added, that the uptake from the soil is the same, is not a valid assumption, at least for these three soils. That's the first implication. Second, it suggests that there is some plasticity here. The corn plant is taking up P from the soil, from say organic P, from iron-bound P, differently when it perceives there to be less phosphorus via the fertilizer, even when the soil test indicates that there's adequate P. Now, this is not a huge surprise. There's ample evidence, like by Dr. Lynch, showing that the foraging mechanisms and magnitudes of crops like corn, they will differ based upon whether or not we fertilize the soil. Now, a question was raised, we had, is there any regression or is there any correlation between the two values of PUE by the difference versus by the method, sorry, by the isotope directly? And the answer is that it did depend on the fertilizer. So when it came to MAP, there was no correlation, but there was a correlation between PUE by difference and PUE by the isotope. It was significant statistically, even though the R squared is a little shaky, right, of 0.63. So this suggests that solubility does influence how well we can have correspondence between PUE by the two methods of determination. We also asked whether sol melic 3P could be a proxy of PUE. And this is shown here depending on the symbol and by the fertilizer, the method of determination, and then the source. And the short answer was that these are not inverse as hypothesized. So it's not the case that as we have more phosphorus in the system, available, if you will, that there's a greater discrepancy. So we did reject that hypothesis. It did seem to be highly specific to the combination of method and of fertilizer, specifically for MAP and for PUE by difference. There was a very weak correlation with PUE decreasing as melic 3P went up. So to summarize all this, my animations are out of order, sorry. PUE is a key metric of how sustainable we are with our phosphorus. We want to have PUE be high for lots of good reasons, from economics of farmers to global finite resources of phosphate rock ore. We on purpose used adequate soil P, soils, excuse me. These were testing above the 25 critical threshold of Melic. And we did that on purpose because that's real world. And we find evidence for the hypothesized discrepancies between PUE by difference versus PUE by the isotope. PUE by difference is the norm, but it appears to underestimate PUE. And it's not predictable by Melic 3P. We can't predict how much we underestimate by the difference approach relative to the PUE by isotope approach. Now, a few caveats here. We have a small sample size, and Melic 3P was a poor predictor, perhaps because it was never designed to be available. How likely you'll see a crop yield response to added P? They're not the same. So, takeaway, the fundamental assumption of the PUE by difference is not valid. Implication, we are underestimating PUE by the difference approach, which is kind of hard to see unless you get the negative value. And we see this a lot in field trials. They're not really published though, because it's kind of awkward to publish. It doesn't make sense. The next steps is, can we scale this to the field? Can we compare the two methods, the isotope versus the difference, and see if there is some relationship at the field scale? Now, the challenges here is that, as I've mentioned, there's a short half-life, and also this is a radioactive isotope. A lot of permits are needed for good reason before one can begin to use these in the environment. So with that, thanks for your time. Happy to take any questions by email, margenot@illinois.edu.
Hey, thanks so much, Andrew. I know you got to go run get a kid right now, so I'm not going to ask you too many questions, but just one quick one. If this scales up and the results are the same in the field, what are the implications in your mind for fertility recommendations?
Well, I think for the recommendations on fertility and for crop production, it doesn't change a whole lot. We have pretty good tools on how to manage phosphorus, applying based upon the export with grain harvest, using a stole test to predict how likely that you'll get a responsive yield. I do think, Matt, that the implications are more for how we think about, how we monitor, and how we monitor P sufficiency, right? So if we think about whether there's a connection between low PU sufficiency and off-farm losses. Well, the thresholds of PU sufficiency may not be that accurate. Now, you could argue that the relative differences in PUE are what we really care about for the loss prediction, and that's a valid point. For me, it's more about thinking about whether it should make sense to talk about PUE being low as a reason to not fertilize. And I think that's where this becomes important. We know that farmers need to apply some peat to replace what they remove with crop harvest, but a lot of farmers get critiqued for the values that we see, like the global study of 16% PUE. So to me, it's more of this intellectual tension between why are we applying phosphorus if we have 16% PUE by the difference? Well, maybe it's actually not 16%, maybe it's a lot higher.
Great, thanks for that clarification, Andrew. And again, thanks for joining us for Phosphorus Science Now.
Sure thing, Matt. Thanks for having me back.